Welcome back. In the previous session, we have discussed about the different types of block codes, such as linear block code, n, k linear block code, and n, k cyclic codes. And all these codes are used in second generation wireless communication systems. Later on, the applications of these two are becoming very less, and the further development has been improved the system for wanting of new technologies. In such a way, we have entered into a new kind of channel encoding strategy called as convolutional codes. So, in convolutional codes, in this session, we are going to discuss briefly about the convolutional codes and its encoder architecture and a few examples of convolutional encoder. With the help of an example, we are going to discuss briefly about its generator polynomial based code word generation method and impulse response based convolutional encoding method. By that, we can understand why this code has been named as convolutional code. In the previous cases, in block codes, we will only describe the codes with two different parameters. One is n and another one is k, where n is number of bits in code word and k is number of bits in message word. And in convolutional codes, we are going to determine this code by the specification n, small k, capital K. Here, the term capital K refers to the constraint length. We will describe briefly about the constraint length in the later presentation slides. And the remaining n, small n and small k determines the number of bits in the code word as well as in the message word correspondingly. By this way, we are going to determine the encoding process of n, k convolutional encoder in this session. This convolutional encoder has been introduced by Peter Elias in 1955 and which has been most widely used error control codes due to its strongest error correction and error detection capabilities, and it is having a good structure and having good performance and efficiency in communication systems. Because of this, the convolutional code has been introduced in third generation wireless communication systems. And it is also being used in satellite communication systems. And in mobile communication, the implementation of the convolutional code has been replaced with the advanced technologies, advanced channel coding technologies like low density parity check codes and polar codes in the forward channel. But in the reverse channel, very few technologies are using the convolutional code itself. The forward channel, reverse channel here refers to Generally in the wireless communication, we are having a base station and mobile station. The channel which is used to transmit the information from the base station to mobile station is called as the forward channel, and the transmission of the data from the mobile station to the base station is called as the reverse channel. In third generation communication systems, both the channels used this channel convolutional encoding strategy, but later on in the fourth generation communication systems, it has been replaced by a good performing scheme called as low density parity check code. But still in the reverse channel, in some technologies, the convolutional code is being used. And in satellite communication, still now, the convolutional codes are playing a vital role in determining the error and correct it. In the block coding scheme, what we face is the encoder maps k bits message block into n bit code word. Actually, in block code, the block encoder will accept k number of message bits and produces n number of bits at the code word, and it accepts this message bit in a block manner, m0, m1 and up to mk minus 1, as we have discussed earlier. And all these blocks are given as a parallel, m0 up to mk minus 1. Similarly, at the output also, the code word is generated as a block. To accomplish this kind of encoding process, we need a large buffer to store the entire message block before encoding, and then to leave all the code word bits, all the bits should be stored in a buffer. So the buffer requirement should be large in the case of block coding. And moreover, due to the large requirement of buffer, and since the data coming from the previous block of the digital communication system, either a source encoder or directly from a formatter, is a serial data. And the serial data has to be converted into a block basis, and this stream of bits or a group of bits should be given to the encoder. For smallest value of n and k, this will not be a biggest constraint, but whereas for large values of n and the large values of k, the time to store each value and time to buffer in serial mode will be a tedious one and makes large wastage in time. To avoid these kinds of disadvantages, instead of block by block encoding strategy, we can directly encode based on the arrival of the serial input from the message data. So in such situations, this convolutional code may be preferred as an alternative to the block codes. And the convolutional codes differ from the block codes in such a way that it uses the memory elements in the encoding process. And the convolutional codes generated by the encoders are non-systematic codes generally. So this is the N, K, convolutional encoder architecture. Here, a frame of k-bit message word is assumed and it is loaded in a shift register which consists of k into capital K number of flip-flops. That means it consists of capital K number of k-bit shift register. Since the k-bit message frame has to be loaded into the convolutional encoder serially at every time instant for every clock ticks, this k-bit shift register requires to be fully loaded with this k-bit frame for after k number of clocks in the case of block codes, but in the case of convolutional codes, it is not necessarily to wait up to k number of clocks to load the k-bit shift register entirely. So by serial loading manner, we can generate the code word accordingly, so that we need not to wait for this k-bit frame to be prepared in a well-structured manner, so that the buffering requirement will be less as well as the time elapsed will also be reduced. And this capital K here is referred to the constraint length, which states that the number of shift registers which are all involved, the number of k-bit shift registers which are all involved in generating the code word. If suppose, if this is the message word of ith time slot, then this will be the I plus 1th time slot, sorry, I minus 1th time slot, and this will be the content at the time slot of I minus k plus 1. And all these constraint length, that is I minus 1th time slot to I minus k plus 1th time slot, if all these time slots, the message bits in all these time slots are involved in generating the code word with the help of modulo 2 logic, then this length of shift register will be called as the constraint length. And this n number of shift register is used to store the n-bit code word, and it is serially shifted out from this encoder. In this manner, the convolutional encoder is constructed in a compact way to avoid block by block processing, and it replaces the block by block processing into serial processing. That's why the large number of memory element requirement that happen in this convolutional encoder architecture. And here we always note that n should always be greater than k. If n is the number of bits in the code word and k is the number of bits in the message word and capital K is the constraint length, the code rate of this k convolutional encoder is k divided by n. Sorry, this is wrong. K divided by n. So here the constraint length of the convolutional code is defined as the number of shifts over a single message frame can influence the encoder output frame. As the encoder with an m stage shift register, the memory of the encoder equals m message bits, that is k is equal to m plus 1 shifts are required for the message bit to enter the shift register and finally come out as a code word. For example, if k number of bits are needed to be loaded into this convolutional code, then it requires k minus 1 time slot to load all this data except one bit that will be represented by the number of states. So here, if m is the stage shift register, then as k is equal to m plus 1, then we can write m is equal to k minus 1 number of states are used to represent the different possible states in the shift register, irrespective of the last input be either 0 or 1. So the number of states is determined by this m number of bits, so that the total number of states will always be 2 to the power of m, which will be equal to 2 to the power of k minus 1. Here there are two examples. Here it consists of two flip-flops, 1 and 2. And here let us assume that if m0 is coming here, m1 will already be loaded here and m2 will already be loaded in the shift register 2. Sorry, I have mentioned wrongly. Okay, no problem. We can assume like this also. Then this code word may be either on this particular direction or in this direction. So at any point of time, it will be in connection with either this path 1 or path 2. And this path 1 will be the code C0 and this path 1 represents the code word bit C1. So for the first time slot, it will be, the switch will be connected to C0, and at time slot 2, the switch will be connected to C1. And here, this is the modulo 2 logic circuit in which each of the bits are being used in determining the code word. For example, the C0 is determined by M0, M1 and M2. And from this, there are two code word bits, so that we can say n is equal to 2. And there is only one input bit, so k is equal to 1. And all the three shifted bits are used to represent C0, but C1 requires only 2. But the maximum will be taken into the consideration for determining the constraint length k. So the constraint length k is determined as 3, since M0, M1 and M2 are involved in generation of C0. Let us come to the second example, in which it is having two message bit options. One is M0 and another one is M1 is loaded here. At that particular point, here small k is equal to 2, and we are having three options here, C0, C1 and C2. So n is equal to 3, and here if you take C0, this one, suppose if this is M0 and this will be at the next time, this will be M2, and suppose this will be M1, this will be M3 for the next time durations correspondingly. Then M0 and M2, only 2 bits are involved in the generation of C0, because even though M1 is used in the generation of C0, anyhow this M1, while the loading of M1, the M2 is parallelly loaded here at the time slot 2. So there will be only 2 shifts, that is M0 and M2, okay, that are all involved in the generation of the code bit C0, similarly C1 and C2. That's why the constraint length k here is referred to 2. And here this convolutional encoder is called as 2, 1, 3 convolutional encoder, whereas in this figure the convolutional encoder is 3, 2, 2 convolutional encoder, and the code rate of this convolutional encoder is 1/2, and here the code rate is 2/3 encoder. And this encoder, convolutional encoder, is called as 1/2 rate convolutional encoder. And here it is called as 2/3 rate convolutional encoder. Let us consider the example of 2, 1, 3 convolutional encoder, which is having a coding rate of 1/2. Since it is having only 1 bit message word and 2 bit code words. And let us consider that C0 is generated with the help of M0 XOR M1 XOR M2, and C1 is generated, C0 is generated by M0 modulo 2 with M2, C1 is generated by M0 modulo 2 with M1 modulo 2 sum with M2. As the 3 bits or 3 shifts are involved in the generation of C1, the constraint length of this convolutional encoder is 3. And the encoder operates on the incoming message sequence 1 bit at a time. So let us define the code word table. So the content of the shift register consists of 3 bits. Let us take M1, M0, M1 and M2, and the corresponding code words produced by the encoder are C0 and C1. So we are having 8 different possible set of contents in the shift register, which produces the code word correspondingly. So let us assume 0, 0, 0, both the code words will be 0, 0. So if it is 0, 0, 1, C0 will be M0 XOR M1. So 0, 1, 1, and C1 will be the combination of the modulo to logic 3. So 0, 0, 0, 0, 1, 1. Similarly, if you take this one, so for the generation of C0, 1 XOR 1 will be 0, and the C1 will be evaluated in such a way that 1 plus 1 XOR 0 is 1, and that 1 XOR 1 will be 0. So in this way, the code word table is being framed. So let us determine the impulse response of the convolutional encoder, and with the help of the impulse response, we can determine the generator polynomial of the 2, 1, 3 convolutional encoder, or we can simply say it as 1/2 rate convolutional encoder. Generally, the impulse response of a system is determined by applying an impulse input and getting the response at the output of the encoder. Let us apply an impulse function correspondingly at time t0, and for all the remaining times the input will be 0. So for the very first time, the content of the shift register will be 1 0 0 0. For this 1 0 0, the corresponding code word is 1 1. For the 1 0 0 0, the corresponding 1 0 0 0, the corresponding code word is 1 1. And for the next time slot, if now generally in the first time frame, the content of the shift register will be 0 0 0, and now we are going to apply an impulse. So a 1 is being applied at time t0. So the content will be shifted in such a way that it will be 1 0 0. So for 1 0 0, the corresponding code word is 1 1, as mentioned here. Then at time t is equal to t1, the input 0 is applied, because at one impulse function means at time t is equal to 0, the value of the signal is 1, and in all other period it will be 0. That is, we are assuming this as t0. Okay, so second time the input 0 is loaded, so the content of m1 is shifted to m2, and the content of m0 is shifted to m1, and the fresh input is loaded here. So now the content of the shift register at time t1 is 0 1 0, and the corresponding code word produced by the encoder is 0 1, which is represented here. And now at time t2, again a 0 is loaded, and the content of the shift register m1 is shifted to m2, and the content of the shift register, the flip-flop m0 is shifted to m1, and a new 0 is coming inside. So the content will at time t2 is 0 0 1, and the corresponding output is 1 1. By this way, this table has been framed, and the corresponding code word at time t0 is equal to 1 1, and at time t1 is equal to 0 1, and at time t2 is equal to 1 1. While we applying an impulse input at the encoder, then the C0 at the input, at the output bit C0, code word bit C0, 1 0 1 is produced, and in code word C1, 1 1 1 is produced. And this will be assumed as the generator sequence of this 1/2 rate convolutional encoder. So let we assume these two generator sequences as G1 as 1 0 1, This is G1 and this is G2. G1 as 101 and G2 as 111. Hence, the corresponding generator polynomials are determined as G1 of x is equal to 1 plus x square, because constant term is scaled by 1, x is scaled by 0, x square is scaled by 1. Similarly, in G2, constant is scaled by 1, x is scaled by 1, x square is scaled by 1. So we can write the corresponding generator polynomials as shown here. And moreover, we know that C is equal to m into G. We can represent this as m0, m1, m2. And this 101, C0 is determined by m0 XOR m2. Similarly, C1 means all the three will be 1. So that C1 is determined as m0 XOR m1 XOR m2. By this way, it is being written. And let us discuss the generation of the code word, encoding of the code word for the corresponding message word 1001. Let us assume a message word, serial message word 1001, and let us discuss how the code word is being generated with the help of generator polynomial. So the message polynomial is written as 1 plus x cube. And the code word bit 0, T0, is determined by m of x into G1 of x. So m of x is nothing but 1 plus x cube, and G1 of x is nothing but 1 plus x square. So C0 will be equal to 1 plus x square plus x cube plus x to the power 5. So C0 will be serially output as 10101. And similarly, the corresponding code word bit C1 is generated with the help of product the message polynomial with the generator polynomial G2 of x, which can be written as 1 plus x cube multiplied with 1 plus x square, which can be written as 1 plus x square plus x cube plus x to the power 4 plus x to the power 5. So C1 will be serially output in such a way that 1 1 1 1 1 1. Now the code word will be generated by assuming the corresponding 2 bits like this: 1 1, then 0 1, the next at the third time slot 1 1, and at the fourth time slot and it will be selected and it will be going on like this. Hence, the impulse response of this 1/2 rate convolutional encoder is 1101 and 11 because this is the impulse response. And the convolution of the inputs corresponding to this impulse response is clearly depicted in the following table. How this 1001 message bit is correspondingly encoded with respect to this impulse response in such a way that if it is 1, the impulse response will be 1101 and 11, and at time t1, this is time t0, the first bit is applied. At time t1, the second bit 0 is applied. Time t1, the bit 0 is applied. So if the 0 is applied, all the shift register will be loaded as 0, so that the corresponding impulse response, the corresponding response will be 0, 0, 0, 0 and 0, 0. That will be represented here. And at time t2 is equal to the time at time t2, the input is again 0. So again zeros are loaded. And at time t3, the input 1 is loaded. So the impulse response is represented from the time slot t3. Now you can do the modulo sum of all these corresponding entries in the table. You will get 1, 1 here. Here you will get 0, 0, 0 and 1, 0, 1. Similarly, you can modulo to addition of all these three will produce 1, 1. And similarly, all these three produce 1, 1. And here we cannot able to proceed further determination of all these three since we doesn't know about the further inputs given to this encoder. So that it is still going on up to the incoming of last message bit. So we need not to wait for all the k number of bits to be parallelly loaded or buffered for the encoding process. That is the biggest advantage of the convolutional encoder, as we have already stated earlier when starting this session. And the specialty here is, this operation involves shifting and accumulation, which is represented by the modulus to sum, which replicates the convolution operation. This encoder is called as convolutional encoder. Here we are just convolving the input sequence along with the impulse response of the encoder. We are calling this encoder as convolutional encoder. In the next session, we are going to discuss briefly about the graphical representation of the convolutional encoding process in three different ways, such as tree diagram, state diagram, and trellis diagram.